It is clear that data has changed dramatically in the last few years, both in quality as well as quantity. And as data changes, so do the statistical tools that are commonly used. And if the practice of statistics is changing, we should also consider the importance of addressing changes in statistics education. As many people have previously stated, we need to move away from teaching purely mathematical calculations and instead focus on statistical inference and the ability to make decisions with data. There are numerous examples that demonstrate the problems of focusing solely on calculations instead of properly interpreting the data. For example, a few years ago, CBS News documented a story about how a medical researcher mishandled medical data, which led to improper medical treatments for numerous patients. And several of those patients did die from cancer. Recently, the New York Times published a story about Amy Cuddy, a PhD psychologist who gave one of the most popular TED Talks of all time, but was later heavily criticized for her work. While she did have small p-values, many researchers have criticized the way she collected, organized, and drew conclusions from her data. In addition, there is evidence showing that Michael Mann's research on the hockey stick controversy, used to predict global warming, had analysis with poor calculations and questionable data selection. Finally, ProPublica has a very nice article discussing how statistical calculations has led to clearly biased sentencing in many states. Ideally, we would hope that the researchers who made these errors and likely took an introductory statistics class would have made better decisions with their data. However, at this time, many introductory statistics classes focus on understanding calculations instead of really making good decisions with data. As Albert Einstein has said, the value of education is not the learning of many facts, but the training of the mind to think something that cannot be learned from textbooks. Unfortunately, there are many challenges to textbook data sets that make it difficult to teach this type of thinking. The curriculum guidelines for undergraduate programs in statistical science emphasize the use of practicing all steps of the scientific method instead of focusing on calculations. They state that all too often, undergraduate statistics majors are handed a canned data set and told to analyze it using the methods currently being studied. This approach may leave them unable to solve more complex problems out of context. Many modern and innovative introductory statistics courses using textbooks have activities and group work. They sometimes include primary literature, data collection, and analysis. However, many leaders in undergraduate education say that is not enough. The best learning experiences typically come from high research-like courses, where students are very involved not only in analyzing data, but collecting and interpreting it. This involves numerous group discussions on how to collect and organize data, as well as determining the appropriate statistical models. Unfortunately, this is challenging to do. As we all know, students dislike uncertainty. They would prefer a clear step-by-step guideline on how to get to the right answer. It is much more challenging to coach students to think creatively and critically, to give them space to explore questions and examine unique approaches to data. It can be very difficult, particularly in larger classrooms, to have deep discussions about uncertainty with data and how it is dependent on the context. And it is even more challenging to evaluate students on their ability to clearly articulate these nuances with their peers. In essence, authentic research experiences are expensive and time-consuming. They are very difficult for large classes to implement, and often, even if a final project is done, it is questionable how many students are truly impacted. Clearly, faculty can give examples of students who learned a significant amount during the final project, but without the deep discussions and the feedback, I question what percentage of the students really had a strong learning gain from a project. So taking these concerns into account, we have an NSF study that forces students to think about the entire process of statistical analysis. It encourages students to discuss and understand the importance of skepticism of data. And finally, students are expected to articulate the impacts of variation that can come from multiple places throughout their study. I'm going to describe to you a freely available online game and corresponding lab activity. I'm conducting a paired t-test with this online game. The goal is simply to determine which car is faster. In this activity, students will each race 2 cars, and the game automatically measures the completion time for each race. They practice racing through an online tutorial, and then they are asked to design an experiment. For the paired t-test, they're asked to identify what is the explanatory variable, the response variable, units, what is an appropriate sample size, think about potential confounding variables, then design an appropriate data collection strategy, identifying which data needs to be recorded, and if appropriate, how will you analyze that data? Here's an example of what a race looks like on this free online game. In this racer game, you first put in your player ID, and then we also put in a group ID, which is usually something the entire class uses. We can run the tutorial or actually start playing the game. Once we're in the game, we can select from a variety of cars, then just hit next, and then choose a track. And the race will start. At the end of each game, you can see your results, and you can go back to the main menu and play again. One of the core advantages of this game is that it allows students in a class to quickly design an experiment and collect data that has meaning to them. Since they understand how this data was collected, they're more likely to think about outliers and unusual observations more completely. While we showed one example, there are actually 3 car bodies, 3 tire types, 3 engines, and 5 tracks. This provides over 100 options for students in designing an experiment. Finally, there are other variables that are meaningful to the student but could cause biases in the analysis. For example, why is it important to block by player? How does the experience level impact your speed? What about the order in which you play? Do you get better if you've played more games? These types of questions and many others provide opportunities for students to think deeply about the importance of context in cleaning your data, and in particular, if any modifications were done that could influence the reproducibility of this study. We also have instructional videos that show them how to use online Shiny apps to better understand their data. When you open the Racer t-test app, you should select your group ID. This is usually the group ID given by your instructor and used by the entire class. You will also need to select a level and a track. Notice that we can also select a box plot and provide summary statistics of our data, in addition to conducting various statistical tests. Finally, if you're interested in downloading the data, you can just click the Racer Data button to download the data you're interested in. The following video is one we have all students watch so that we can clearly discuss the importance of data cleaning. This class played the tutorial on the tutorial track. We see that there's a few outliers here. We also see, if we look by player ID, when we look at this data, notice that the clean data is checked. And in this clean data, every single person has exactly 2 cars. These are the first 2 cars that they raced under the correct conditions. If we look at all data, notice that there's a few people in this full data set that played only one game. For example, Forza 2804 or SSL. We can individually decide, well, we just want to move SSL and maybe we want to remove a jab. We also want to remove this person. So we can clean our data set by looking at which players maybe shouldn't be in the data set because they didn't collect the right data. An easier way to do this is just to click the Clean Data option. The other thing we can do is only look at good drivers. The good driver data is only people who properly played the game and then also stayed on the track the right amount of time. They didn't go off the track, and they raced both of their cars at relatively fast speeds. So you see here, if we look at the finish time for some of these players, if we look at only the good data, we will eliminate a few of these people who took a really long time, much longer than needed to complete the race. See, our finish time has dropped dramatically. Now we have a very nice clean data set where we can run a two-sample t-test or a paired t-test, but as it says here is the error, we can't do a t-test looking at all the differences here. We need to change the x-axis to body. And now we can do a paired t-test or a two-sample t-test looking at the differences between the Bays and Nightingale cars. After playing the racer game and conducting an experiment, students can see the importance of data cleaning, sample size, and reproducibility in your research. We build on these themes by having students read the following articles. It helps them understand how the techniques we discuss in class using a simple game are also very valid in current research. We also ask students to read the ASA statement on p-values. Here are a few of those statements, and students are asked to make connections between the ASA statement and the class activity. One of the most surprising results of this activity is that student feedback consistently says it is so nice to finally conduct a real study in our statistics class. We use textbooks that we thought were using real data. But with this game, we are not working with a clean and vetted data set. Students need to make their own decisions about what to do with outliers and unusual observations. And in addition, instead of just saying the p-value is small or large, they have to say, do I think this car is better? Do I have enough evidence for that? So they have to put the p-value in a very different context. What we find is that students are much more careful to draw conclusions when they have collected the data themselves. These online activities make it very easy to incorporate a research activity or an experiment into a class of almost any size. We also try and connect this activity to real articles, and students quickly see how they can apply what they've learned in the game to published articles in various disciplines. In addition, students tend to be eager to develop additional experiments to improve their gameplay. And in our assessments over the past few semesters, over 95% of students suggest we continue to use this activity in future courses. We have several more activities that are available on this website. Please don't hesitate to contact me if you have any questions or if you are interested in class testing any of these materials. Thank you for taking the time to watch this video.